I'm Professor Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. Today I want to spend a few minutes delving into Gibbs Free Energy because it's one of the most important ways that we look at energy in biological thermodynamics and chemical thermodynamic systems. And the goal is to motivate looking at Gibbs Free Energy and how it gets to something that you would say we start to use a ton in biological or chemical systems, which is equilibrium constant. In fact, oftentimes we synonymously think of the Gibbs Free Energy in its relationship to this. And so we're going to spend a few slides just looking at some build-up to this so that when we start talking about equilibrium thermodynamics and looking at chemical reactions, biochemical changes, etc., in terms of equilibrium constants, we'll have some background and context for this. So one of the things that quickly comes up is you see a lot of things that the molar free energy is, the chemical potential, or a lot of times it gets thrown around between free energy, Gibbs free energy, and chemical potential, and really, what's going on between them. And this all stems from, what we start as, like I've always said, like one of the only things I truly remember as far as equations in thermodynamics is what I think of as kind of the combined first-second law. But one of the Legendre transforms, or transforms to a different type of energy besides internal energy that's extremely useful in the biological and chemical sciences, is the Gibbs free energy. And this is a Legendre transform on both PV work, mechanical work, and heat. And it switches the dependent variables from internal energy of entropy, volume, and number of moles to temperature, pressure, and number of moles, as we've seen here. So, and one of the reasons this is so critical is that a lot of times in biological systems or chemical systems, we'll often hold temperature and pressure constant and watch a reaction. We will do something medically at a fixed temperature, say 37 degrees Celsius body temperature, and a fixed pressure roughly of about, an atmosphere or so. The pressure changes, within your body are fairly small. The temperature changes the same. So oftentimes these can be considered to be constant. And then really look at what is changing about the number of moles or the constituents or composition of a system, what type of reactions are going, what type of forward and backward changes in a system are happening. So this is how we build thermodynamics. And one of the things we said, because this energy, just like the internal energy, is a state function, it's independent of path, we can use exact differentiation. We can expand this as a set of three partials, where I've just listed, the partials here that we're looking at. So we can look at it, with respect to temperature, pressure, and number of moles of a system. And this one, as we can see from the equation above, is related to the entropy. This partial, how the Gibbs free energy changes with pressure, is related at constant temperature and number of moles, is related to volume. And the one that we're going to really look at today, because we're often holding these constant, is how the Gibbs energy changes with the number of moles, how it changes with composition as a function of fixed temperature and pressure. And that goes as the chemical potential. In fact, we often say that the chemical potential is the molar Gibbs free energy of a system. So when we're looking at this, it's oftentimes now, instead of just looking at, where we use a capital N to say that, the fixed composition, in other words, that kind of almost implies a single component system. Now is when we're really going to look at what we've shown all along, but we really haven't addressed, which is we're really summing over multiple components of a system. So the ith component. And so I've made a small version here. So, this, for example, is classically, would have four components. Some component A some component B in the starting mixture, and it could react to form C and D. So at any one time, we could have up to 4 components. So we could write this as, instead of just generically as the sum, we could say it's the number of moles of each of those components, right? And oftentimes we go from a capital N, which is often used to say the total number of moles or indicate the total in something. We often use a small n and then the subscript of which component we're talking about. However, you'll also see me every once in a while use a capital N and a superscript A kind of interchangeably here. So again, now we can look at this, and so now we can write out the fundamental equation for Gibbs free energy as the heat, the mechanical work, and now this chemical work term, where we write it out as all of the individual components for this specific system, one that has 4 components associated with it, A with its stoichiometric coefficient, sub A, B with its stoichiometric coefficient, etc. Right? Now, just integrating from something that we started with no number of moles of anything to start with, so we would have 0 free energy, right, associated with it, to whatever state we're talking about, and so that's going to give, G minus 0, and then we can integrate over from Z, we start with nothing, no number of moles of anything, to the number of moles of each one of those components, right? So it'll come through here, 0 to NA, 0 to NB, etc. And, it gives this relationship. And so, this points out very explicitly how the Gibbs free energy is this, chemical work of just adding up each of these components associated with it. So that kind of gets us to this point and helps explain each of these components. Now let's look at it in terms of something we're familiar with, which is, so we're doing this reaction, A and B, two, with their molar coefficients, going to form C and D. Like, for example, 1 mole of A reacts with 3 moles of B, some compound, to form 1 mole of C and 4 moles of D. So we start, with 1 mole of A here, we start with 3 moles of B here, and, they react, and, what ends up, are 4 moles of D and 1 mole of C, right? And what we want to look at is what we mean by this extent of reaction. So, and we use this to set up a lot. So, we know the 2 end states, if this reaction is spontaneous. So if we could say what the end states are if we go 100% this way, right? Which is this is showing. We can look at constant, and we'll do this at constant temperature and pressure being constant, so that we're only looking at the chemical work term here. And we're going to define the extent of reaction as how each one of these changes, the number of moles of each of the constituents, A, B, C, D, change over their stoichiometric coefficient, or keeping track of how much each one of them are. And we're going to realize that anytime A is formed, if C is formed, it's at the cost of A and B, and same with D, right? So they're going to come negative associated with those, right? And so now we can define it in terms of not how the number of moles changes, but the extent of reaction based that the number of moles, they can't change randomly. You can't just randomly add C to it. It's only because of the combination of A and B that can do it. So taking into account the chemical formula that defines it. And this now allows us to measure out this extent of reaction. And so where we want to get to this, and this is what we're, one of the driving forces for looking at this extent of reaction, so to be able to follow these individual components, right? But now we can say, how does the Gibbs free energy change as a function of the extent of the reaction? And this is something we already have a feel for, which is we know because of the maximizing of entropy based on the second law, that energy is often minimized in this process. In fact, you can show, we've shown this in the lecture notes, etc. And so this gives us a way to, find this minimum when this extent of reaction or this change, is happening here and here, but it comes and we find, the equilibrium, in the system. And you can see based on how we've set up this extent of the reaction, and this is starting to look familiar. CD minus AB. In other words, if you start producing C and D, they come at the expense of A and B, right? Because we're looking at a specific case in this, right? So this will change depending on what your exact reaction stoichiometry or equation is. And this gives us a preview of where we're going. We have a sense for what the equilibrium constant is from general chemistry, general physics, et cetera, mainly general chemistry and biology, that we know it's kind of the products over the reactants. And you can see that this is heading in this direction, the products here, over the reactants. And it's going to come, these are going to get over each other instead of being a difference because of this natural log that comes up. And the way I kind of motivate this is we often start looking at these reactions in the gas phase, right? And so if we look at it in the gas phase, we know that, the change, so we can look at, gas pressures, for example, and we can, integrate, over this, this will be, if it's an ideal gas, will be, nRT over P. In other words, P comes inversely to this, which is what gives this natural log. So you can see where we're heading with this. So for something, that we often start with reactions, just simple gas phase reaction, treat them ideally, we can look at the Gibbs free energy. It will go as, nRT over the natural log of the pressure over your initial pressure, we often call P0, right? And so you can see where this is heading. We can also say that this is because we can make this relationship that this is, the chemical potential minus the initial standard state chemical potential, right? This will go, more or less with this same relation, except the N, because the chemical potential is the molar free energy, so it'll just go as RT ln of P over P0, right? And so we can see, that we're heading kind of in this direction, that, and what you're going to have is a series of partial pressures of the different constituents over each other, and those are related to the mole fractions or the concentration or the amount of each one. And so this is kind of where we're headed theoretically in this way. So in summary, really, where does this head? The concept that the free energy, which we use extensively in biological and chemical thermodynamics to tell us about the spontaneity of a reaction, or if a reaction is at equilibrium, right? Or if it's spontaneous or not spontaneous in some direction, right? And we often do these at constant temperature and pressure so that we're just looking at the chemical work term. And this Gibbs free energy, because of it being an exact differential, really relates down to the equality of the molar free energy being these chemical potentials. And it's really the chemical potential of things to react or change that we're most interested in the system. So I hope that gives you an overview of kind of where we're heading to an important concept that we already use in chemistry and biological sciences all the time, which is the Gibbs free energy to look at reactions or any type of biological or chemical process. Its relationship to the fundamental concept of chemical potential and how this is eventually going to relate to equilibrium constants, which is often how we express or use chemical potentials or free energies a lot to look at equilibrium, to know which direction reactions are heading or where their equilibrium is more towards products or more towards reactants, et cetera. Thank you.